Hello everyone, welcome to the latest in our series of webinars on partial discharge from EA technology. So we're going to get right started into it today. So today the topic is we're looking at managing partial discharge more in industrial networks. It's the same principles, so anybody from utility or any other industry, the same principles apply. We're just going to bring out some examples and some case studies that are more targeted towards the industrial aspect of people's networks. Okay, so just a question just around the questions during the webinar. So we will answer the questions. I've got Thomas White, who is sitting alongside me here, who will be monitoring the questions. We'll take some of them in the presentations, and we'll also type some of the answers out. Everybody will be able to get the Q&A at the end of the session. So if you click the orange arrow to answer to ask any questions, you type them out there, and we will deal with them as we go. Okay, so the contents of the presentation today, we're going to very briefly discuss condition monitoring and what is partial discharge. We'll talk about the classifications and the different ways that we actually detect, so the detection techniques. A lot of this will always will bring out examples. So examples using the handheld, some case studies, and what we use for the interpretation and how we can use that to help prevent failures. We'll then just talk at the end towards why there is a definite trend towards permanent monitoring or more cases of monitoring, and again some case studies on that, and show you how the risk is reduced if you put permanent monitoring onto the net onto assets as well, switchgear and cables. Okay, so like I say, any questions at any time, shoot them through, and we will also have a session at the end where we can take anything further. Okay, so why do we test for partial discharge? And simply, it's around three aspects, which are all very much intertwined. So, of course, when we've got high voltage assets in there, if something disruptively fails, as you can see in the two pictures here, then we do have a safety aspect. So we don't want to be standing in the substation, we don't want to be in the switch yard when something disruptively fails. So if we can prevent that failure, or we can identify something that is under distress and is starting to break down, we can increase our safety performance. So always number one. Of course, improving the asset performance, if we stop things blowing up, we're going to have better availability, we're going to have better asset performance, longevity of the assets, and that's going to give us both the safety aspect and also that financial benefit at the end. So proactively going in and fixing something before it fails is always a much lower cost than waiting for something to fail, waiting for something to fail of any significance and fixing it afterwards. When we have production issues in the way, then the financial benefit, depending on the criticality and how much production is lost, becomes an even bigger aspect. Now, partial discharge, based on the number of failures of switchgear, we would estimate to be around 85% of unexpected substation failures are due to insulation failure, and insulation failure was typically precursored by partial discharge activity. So if you're going to do one sort of condition monitoring for high voltage assets, then partial discharge is going to give you the best benefit, increasing the safety and improving performance. Now let's just step back and take a brief overview of the different maintenance strategies. So different equipments that you have on networks may require different strategies, and generally people will do a risk assessment taking into account the risk of injury to staff or to the public if it's people get access, the impact on the network operation, the replacement costs, material, lead time and everything, and the consequential damages or losses. So if we were to lose a particular cable or a switchboard and we can't get that back in for a period of time, it's how much production maybe have we lost, how much is that going to impact on the network. So maybe in a petrochemical plant in the wrong place, it caused major disruption through the network. So that's typically what you would do for all the assets. And then you've got three basic approaches to maintenance. The most simple and probably least effective is just maintenance based on failure. When you have maintenance based on failure, that may be appropriate for something with very limited consequence, but it is not typically appropriate when you're looking into high voltage substation switchgear or cable type assets. Preventative maintenance is traditionally what used to happen, which is the every now and again, based on maybe manufacturers' recommendations, you'll be taking switchgear or plant out of service and looking at the and looking at it on a periodic basis. That may not be the most appropriate in terms of you're opening things up too frequently. You may be introducing defects, and it may not be the best use of your resources, time and materials. So the trend throughout the last number of years, the last couple of decades, has been to get maintenance based on condition monitoring. So looking at the condition of an asset and finding out when we actually need to intervene, what we need to do in order to keep that asset running reliably and safely, and getting the best value from that. Where we've got industrial sort of situations where we only have periodic outage availability, then it can become a mixture of those bottom two. So we will carry out condition monitoring, and based on the results of that, we will then target the maintenance in a specific time. So that is really the way that we like to run networks where we've got specific outages. So let's start with a case study and show you one example of where that approach proved extremely valuable. And this one is in a company called Davies, so a petrochemical organization in the United Arab Emirates. And this organization had a very high critical switchboard. It was an 11 kV switchboard, and the whole plant effectively running off that. Now, their shutdowns happened once every 4 years, and in this particular switchboard, if we had a failure in the wrong part of that switchgear, there was calculated losses of a minimum of $15 million if that switchgear failed. Now, the organization knew that they didn't have a way to test the installation, so they instigated a program of partial discharge monitoring, non-intrusive monitoring, to look to see if there was any issues that they needed to address during that outage, which happened, like I say, every 4 years. Now, the application of the partial discharge monitoring in this particular instance found that there was partial discharge activity coming from the area of the bus coupler. So probably the most important panel on the most important switchboard on the whole plant. They found that they had PD signals. So prior to that shutdown happening, they were able to get themselves ready. So they had spare components purchased and ready to go. They targeted the activity. So they opened up the bus bar and the bus coupler area, which is something that they would not typically have done during the maintenance period. So they were able and ready and in a position where they could go after that issue during the shutdown. So they opened up the bus bar, and the picture on the bottom left shows you the bushing that was in the bus coupler. This had just a small level of insulation left, so it was about 70 millimeters of insulation left before it would have failed. So this would almost have certainly failed between the outage period here and the next 4 years if it hadn't been addressed. So they used that condition monitoring in advance of the shutdown to target their activity, to get the components in time, because they've got a 2-week shutdown every 4 years, and to replace that, and they never had any issues. So that's a minimum of a $15 million loss. In that particular instance, where it was on the most critical component of that switchboard, that could quite easily have expanded into many more millions of dollars on top of that, especially if you were able to get the components easily and quickly. So let's step back and think about the different types of partial discharge that we get. The one that we just saw was a surface discharge. So surface discharge is something that's tracking on the outside of the solid insulation. Eventually you will get a path alongside that insulation carbonized from the high voltage to the ground, and that's where we get the flashover and failure. There are 3 main types of classifications of partial discharge. The surface discharge we've just shown. The internal discharge is something that is happening deep inside the solid insulation. These are often the most difficult. During a maintenance period, if you were to open something up, you could potentially see surface discharge. If you open something up and something is happening deep inside the insulation, you'll have no visual indication of that, and therefore you won't target activity towards that. So it's possibly the most dangerous type of defect that you can come across, because you don't get that prior warning based on visual or other sensory indications. And the third main type is corona discharge. Corona discharge is where we are going from a high voltage point into a gas, usually into air, so a sharp point into air. Depending on where that is, that can be destructive or non-destructive. So on a high voltage open yard switch yard, that typically isn't much of an issue. If that happens inside more enclosed space, say inside a switchgear panel, then that can break down the atmosphere in that panel, produce nitrous oxides and eventually nitric acid, and start attacking additional insulation and cause you a problem. Of course, there are always hybrid sort of things as well. So one of the common defects that we do come across is like an intermediate state between a surface and internal discharge. So this is the one on the left here. It's like a contact type problem or a floating metalwork type problem. This one gives us characteristics which are similar to internal void discharge, but can also sometimes happen in a very high repetition rate, which is similar to a surface discharge. On the right hand side, we get the one which is a combination of the surface and corona. So this is where the corona discharge starts affecting the surface of other insulation, and we get that hybrid as well. So all these different types of PD classifications can occur, and depending what type it is and where it is, that will change our target different maintenance activities and change our interpretation and diagnostic of what we need to do. Luckily, we can detect all of the different types, and the way that we detect the different types of discharge are using a series of sensors that are operating at different frequency ranges. So we use a capacitive sensor, which is the top left picture. A transient earth voltage sensor works in the HF to VHF range, 2 to 80 megahertz. That is specifically designed for detecting internal discharge or any high level of surface discharge which is going towards earth. Ultrasonic microphones are used in the top right picture, either an airborne microphone, which we're showing here, or a contact probe. which is also used, that detects surface discharge activity on air insulated components, so tracking across the surface. So we always use those two techniques. If we're trying to look down the cables or determine is it specifically discharge that we're finding around the cable area coming from the cable termination, maybe the switchgear, or is actually traveling up the cable, then we can deploy a HFCT or radio frequency current transformer, detect the high frequency current pulses that are coming up from cable discharge. So you can see that in the bottom left in the same instrument, we're detecting that there. And when we're going into more high voltage or EHV type yards, or where we have where we can't actually physically touch an asset or unearth part of the asset with a TEV probe, then we can use a UHF type antenna. So on the bottom right picture is a directional ultra high frequency antenna using, again, into the same instrument, and that will detect stuff that's happening in these high voltage yards, and will also be able to ignore corona activity, which can cause interference issues in that sort of environment. So all of these techniques are deployed depending on the situation that we're in order to find that different type of discharge on all the assets. So where we actually do use it, so for the enclosed switchgear, metal clad switchgear, we typically use the TEV and the ultrasonic. That's the primary techniques for that. When we go into open terminal type equipment, overhead lines, we'll use TEV, ultrasonic, and UHF, where we want to ignore the coronas and we want to do things from a distance. For transformer and switchgear cable terminations, we will apply all the different types of techniques in order to figure out where exactly things are coming from. Cable circuits, again, use the TEV, and we use the HFCT and UHF at times to see if it's local. Ultrasonic becomes less of an issue when we're actually detecting things happening inside a cable itself, because we haven't got any air path in that particular instance. Okay, so what we're going to show you now is some examples and the interpretation. So how we've detected different types of discharge using the different techniques, and the interpretation behind that, so we can target the right maintenance and intervention to prevent our failures. So starting with internal partial discharge, like I say, probably the one that if you were just going to do a visual maintenance and you're going to open things up, these are the sorts of things that you just will not see the defect. So if you're just purely relying on visual examination, these are the failures that will come in unexpectedly and cause problems. So the first one, we've got a few examples here, all revolving around transformers, but with different interpretations and different defects. So this particular instance, we were using transient earth voltage, so TEV capacitive coupler at the bottom of a cable termination on this 22 kV transformer. The equipment was able to give us a phase resolved plot, which is a representation of the amplitude of the partial discharge activity in reference to the 360-degree sine wave based on the 50 hertz in this particular instance. And you can see that we've got two clusters of activity happening 180 degrees apart here. And the number of pulses per cycle is relatively low. It's about 2 to 3 pulses per cycle. All this gives us a very good indication that what we're seeing here is internal discharge inside solid insulation. It's at a level, so up to 38 decibels of where we're worried about it, so it's quite a high level, solid insulation. So what we were able to do in this particular instance is use some time of flight measurement equipment, which we'll talk about in a couple of slides. And we were able to narrow that down to one of the phases and a joint that was on the top of the cable tray going towards that bushing. So we were able to confirm in that we've got a joint which is discharging, going to the transformer. So during the maintenance activity, then our recommendation would be to take that joint out and to re-terminate in that location. The next example is again on a transformer and again found using the transient earth voltage technique on the outside of a cable leading into the transformer. But in this instance, we've got a different type of phase resolve pattern and a different level of discharge and pulse rate. So in this case, we have 26 decibels and we have about 15 pulses per cycle, so much higher discharge rate. And if you look at the pattern of the PRPD, here we've got a slightly or a very much more distinctive different type of pattern where it's two clouds, again, 180 degrees apart. When we see something like this on an oil bit of plant, whether it's transformer or switchgear, we start suspecting that we've got discharge inside the oil chamber itself. Time of flight was again deployed, and that indicated that the signals were coming from up towards the cable box towards the plant rather than from the cable itself. So at that particular instance, we can't determine, is it the cable termination, is it something to do with the bushings, or something to do inside that oil. The pattern and the number of pulses lead us to suspect the oil. So at that time, we take an oil sample from this distribution transformer. That oil sample also indicated high levels of the acetylene, so we've got partial discharge going on inside of that. So the actual maintenance activity, this particular instance, is actually replace that transformer. For this particular site, the cost of the transformer and the criticality against the process, the easiest way to do it during that shutdown was to actually replace that transformer. So as you can see there, we found discharge activity on the outside of cables around a transformer, and we've got two very different sorts of defects. One's on a joint, one's inside the transformer. And if you can quite easily jump to conclusions, and this is where people sometimes fall down. Probably the biggest failure mode of parts on switchgear is cable joints. So is the terminations. So people often will jump to the conclusion of just replacing a termination and maybe carrying out some activity which is actually not relevant and is not going to solve the problem. So one of the things that we actually use in order to narrow down where things are coming from is to use a process of time of flight measurements, so where we can determine where exactly the signals are coming from. So you can see just in this the picture in the slide here is a representation of partial discharge we found across a switchboard, and the red boxes are where we find high levels of transient earth voltage activity. So you can see we've got three panels where we've got high levels of activity, and it's going across multiple components from the circuit breaker, TT chamber, cable box, and cables. We're finding high levels. So what we use time of flight for is to determine where the source of activity is, and is there one or more more discharge sources on the board. An example of that is in this case study here. So originally, in this particular instance, we carried out a partial discharge survey on the switchboard, 11 kV switchboard, and temporarily installed a monitor for a period of 1 week. So as you can see on the 12th of August, where we carried out the installation, we carried out the survey, we actually found no levels of partial discharge activity at all. Then by the 13th, we've got this high increase in the level of activity. So something has switched on. So process switched on, and we were able to find, or we're seeing high levels of discharge. we can see it then subsequently switches off around the 15th and back on the 16th. That switching operation gives us further indication of where that discharge may be. And it showed in this particular instance it was associated with the circuit side of one particular panel, the bus bar always being live during that operation. So it's the circuit side of that specific part of the switchgear. Is that the location? Unfortunately, what you need to do is a little bit more investigation to know where to look. So we do that using this time of flight locator accessory into the instrument, and we were able to start tracing where the signals were coming from. So actually, when we were doing the measurements at the back of that circuit breaker towards the cable, it was saying that the cable was the signals were being found on the cable first. We traced that cable through. It was just a short 10-meter run to a set of intermediate circuit breakers, and that was this time showing more towards the intermediate circuit breakers than the cable. We then go to the back of those circuit breakers where it's moving towards the transformer, and we can see it's moving away from that, and the higher signals and the location were actually located to a transformer cable box some 30 meters or so away from the circuit breaker where we initially found the problem. Quite interestingly, in this was in a steel works facility, and that transformer box had disruptively failed in service previously. Once it disruptively failed, there was a big rush in order to get that back on so we could get the production back up and running, and it was fixed. It was put back into service, and what had happened is the work had not been done to the necessary level of standard, and we were finding another discharge problem coming into that termination box. So a further failure would have occurred. So what we've actually done in this instance is we found that the discharge was happening and the repair was not optimal, or had not had the desired effect of removing the defects, and this secondary defect was then planned in for replacement and doing things in a much more planned and orderly manner during the next outage, which was coming up at Christmas time. That was done, and the second failure was prevented. So just because we're getting things in the circuit breaker, we do have to do that little bit of investigation to see where things are coming from. So when we're talking about transient earth voltage, the interpretation of these TEV measurements, we do take into consideration the number. So on that last example, 42 decibels is a high level, 38 on the other transformer is a high level. So once we get above certain levels, we start paying much more attention and start indicating recommendation that we really go in there and find what's happening. The PRPD plot, the phase resolve plot, helps with the diagnosis and the certainty. So we were able to say one was a solid insulation, one was inside the oil, and we used the time of flight in order to locate where things are coming from. As I say, during a visual examination, you may not always see a defect. If it's deep inside the insulation, such as what we see in these bushings here, then it's going to look okay from the outside. But you have to be aware that where things are coming from, and replacing this bushing will prevent a failure, even if it looks okay on the outside. Okay, let's move on to surface discharge. This is an example of a defect that was found inside a voltage transformer using the ultrasonic testing technique. The phase resolve plot actually shows that we've got two phases involved based on the pattern here, and the sound characteristic was associated with partial discharge here. So this is an indication that something is going on inside that voltage transformer. That's not something that you would typically open up during a planned shutdown. But in this instance, because we've seen that problem, or we've indicated that problem, that is something that you would then target the activity during that maintenance period, and find that problem, solve it quite simply, and prevent that unexpected failure. The next one is on an overhead termination. So from ground level, using a parabolic dish, in this particular instance, we were able to see that we've got discharge occurring. Due to the pattern, we're able to see that it's multi-phase, so it's phase-to-phase type discharge. So the terminations, the spacing between the sheds of these different phases in the high stress area is not adequate, and that is causing discharge activity, and again, something that we need to address. So surface discharge activity is generally very easy to identify exactly what's going wrong once you've taken that outage, or once you've taken the opportunity to look at it during the maintenance. The main thing with this is to target which chambers to open up and which are appropriate. Okay. I don't think the sound's coming through, sorry. Okay. Just one thing to be aware of with ultrasonic measurements is that things typically do not accelerate away. You don't tend to see an increasing level of ultrasonic as things move towards failure. So in the top right-hand picture on this 11 kV circuit breaker, we've got maybe 20, 30 or so millimeters of insulation left. A level of discharge was the same as when we go to the bottom picture, where we've got 1 or 2 millimeters of insulation left. So there is no general upward trend, and the level of humidity in the atmosphere will always dictate how high a level of partial discharge that you hear. So for interpretation of ultrasonic or surface discharge measurements, trending is not the main thing to do. It's more important to listen to the sound characteristic, look at the PRPD, and take a visual examination to understand the level of degradation, and to see that you've got these problems. The quicker you intervene, the bigger the chance of having a very simple fix. Once things have accelerated away to a large level, such as maybe in this particular instance, you may need to go into the situation of replacing some of the insulation components. So what do you do if you take you carry out a partial discharge survey, and you're finding indications of partial discharge? Now, if you can isolate the suspected circuits, all well and good. That often depends on the criticality, whether you can work around it, or whether it is more critical to production. If it's a surface partial discharge problem, you can look at controlling the environment. Reducing humidity will slow further deterioration and maybe buy you time until you can get that outage or your shutdown is coming up. We always recommend keeping the system stable, so reduce switching. When you carry out switching, you'll get switching surges. That may be the final straw that breaks the final bit of insulation and causes that failure. So keeping things steady until you can get that outage is another good thing. Or if you switch something back, if you switch something out, be very careful when you're switching something back in. As a safety aspect, limiting access to the substation or time spent near the suspect asset. So that's just about minimizing the risk to people in case that disruptive failure happens. If you have indication of partial discharge, get ready, plan, so that if it does happen before the outage, before your shutdown occurs, you can limit the impact of that failure. So in the AdGas environment, they had contingency plans ready, they had the components ready. So if it had disruptively failed before they took that outage, they could try and minimize that outage time. And another thing that people do is to install PD monitoring, to almost nurse it through by looking what's happening until positive action can be taken. Is it deteriorating? Is it causing other? Is it starting to trend away? The difficulty, of course, with that, with the ultrasonic, is you don't get that positive trend. But if you're reducing the humidity in the location, you can see that things are not deteriorating at a particular time, or they're deteriorating at a slower rate. So monitoring is a way of helping manage that risk. There is a definite trend towards partial discharge monitoring on switchgear and cables as a method of risk reduction. So a couple of quick slides on that. The benefits of monitoring, of course, it will capture things that happen in a much shorter P2F interval. So the P2F, the point at which you can detect a fault versus when it fails. Typically for discharge, that P2F interval is quite large, but we have found some instances on surface tracking, at least, where the period from when you can detect a fault until when it actually fails is only a short number of months. So that's not the sort of thing that you'll capture all the time using an annual survey. Monitor will help you find those short time problems. As we showed in the transformer cable box, the network conditions, things switching in and out, can change whether discharge is detectable or not. Environmental conditions can do the same. And the quicker you go in, if you can actually intervene before any set time, the more early warning you get, potentially the easier fix. So people are tending to put the permanent monitoring on more critical switchboards, any high consequence of failures, where there is staff safety. So if people are working in a substation for a period of time, then maybe permanent or temporary monitoring on that while it's happening. And just reducing the risk exposure on older plants when you're trying to extend the life of that plant. All these are reasons why people are starting to move more towards permanent monitoring. So a case study example of that, this is a transient earth voltage and ultrasonic monitoring system. The ultrasonic sensor is pointing in the red circle towards an air insulated cable box. There was many months of absolutely nothing happening, and then all of a sudden we have an increase in activity on this sensor, which goes above the alarm level. Looking at the graph here, we can see we've got very low levels of activity happening, and then all of a sudden something starts happening. It sticks its head up, and we can inform the customer on that. We can go on site and we can confirm exact locations using the handheld equipment and confirm with the PRPD that we've got surface discharge occurring inside that cable box. So it wasn't urgent. It had only just started happening. So we were able to wait until at least another couple of months. So we had a planned shutdown coming up. So 2 months later, able to open up that cable box. The inspection revealed that there was a problem with the cable termination, and we had reduced clearances just where the semiconducting layer is coming off, so in the high stress area. So in order to prevent that was a case in this instance of just cleaning, increasing the clearances, so taking that clearances until it was adequate. And then we've continued to monitor since that remedial work. So quite a simple fix in this instance, and the discharge activity has gone and it's not coming, it's not returned since that. So that monitor has enabled very quick intervention and a much easier, simpler fix. So how does partial discharge, whether it's handheld or monitoring, actually reduce risk? And if we look at what the risk variables are, the asset condition is dictated by maybe maintenance strategies and the type of equipment you've bought. Where we're really targeting the risk reduction for partial discharge testing is to reduce the probability of failure through condition monitoring, periodic or online monitoring. The reason where the monitor will increase or further decrease the probability of failure is that you're monitoring over that 24/7 rather than just once every year. So the more frequent you're monitoring, the more you will reduce that probability of unexpected failure. Of course, if you can change the criticality with network configuration, the consequences, there are other ways of reducing the risk on your network of particular types of assets. So just to give you one example, this is one where we've done a calculation. The right-hand blocks here are showing you a particular switchboard under different types of condition, in average condition when it's new, right the way through to quite old, towards end of book life, and then to starting how it's starting to degrade. And the right-hand block is showing you the level of risk that this particular organization was running on that switchboard compared with a monitored solution, so a monitor installed on the switchboard versus something that wasn't monitored. And you can see that even with aging assets, as we're moving that up past end of book life and starting to get some level of degradation, a switchboard with a monitor on is actually running less risk than the unmonitored switchboard when it's much newer. So this is how people can use partial discharge or permanent monitoring in order to reduce risk and extend the life of the assets and replace them at the optimal time. Okay, so in summary, the application of partial discharge, whether it's periodic testing or monitoring, will improve your asset performance, and it will give you greater reliability and safety by reducing that probability of failure, in now enabling you to target your maintenance activity at the right time. And this can reduce, will lower the cost. Obviously, the cost of intervening is much lower than the cost of fixing a problem when it occurs. And if you've got the big penalties, such as in the AdGas situation where they would have had a minimum $15 million, then the cost of implementing a condition monitoring program is just a very, very small fraction of that. It also allows you the smarter investment decisions. Will this switchgear, will this cable, will this network last for another 10, 15 years? Give you an indication of how things are traveling and maybe when replacement of assets is necessary. So using partial discharge can have a great benefit to organization in terms of meeting their financial and safety objectives. Thanks very much for listening. Have we got any questions, or questions are not happening?
Suspiciously, I have 0 questions.
Suspiciously, we have 0 questions, Thomas says. So it's either very unusual or something has gone wrong, which is not that unusual. It's happened once before. What we do have here is our contact details. Oh, here we have one question come through.
What can cause internal discharge in solid insulation?
Okay, yeah. So what can cause internal discharge in solid insulation? This is often manufacturing, or it can be manufacturing. Say if it was in old pitch-filled boxes, the way things are poured in. Some of the issues we've had in older cast resin type current transformers, for example, would have been whether it was drawn down under a vacuum, so voids can be left in during that manufacturing process. When we're looking at maybe cable joints, cable terminations, then it can be a case of not following the instructions properly, or just workmanship defects that leave solid insulation voids in there. What you find with a lot of solid installations, you might get very micro, very small voids over a period of time as the insulation ages start building up until they start combining, and then you can start getting internal discharge. So what may start out as acceptable or very small can over the aging period of many years start aging, and that internal voids can build up and cause problems. Okay, the limitations. So what are the limitations on this technology, if any? Is it more superior to offline PD test? They all play the part. So the good thing with online type testing is you're testing things as they are in service. Everything is running as it is. It's three-phase testing, which is often offline testing is single-phase testing. You're testing the cable terminations. If you're doing offline testing of, say, switchgear, then typically you cannot test the cables, because if you're doing 50 hertz or 60 hertz testing, you cannot test your cables because of the capacitance, unless they're very short run. If you're doing VLF testing of just the cables itself, then you may not be testing all of the termination. So offline testing has its part. Offline testing can be very much more sensitive to finding very small levels, but often the case is you're finding small levels of discharge offline testing, which are not particularly going to cause you immediate problems. So the technology, the application of non-intrusive technology is very much easier to deploy. You can test a lot more assets a lot quicker, and you can find the things that are likely to cause you a problem in the short term. So they both play their part. Okay, is arcing in transformer oil classified as internal discharge, detected the same way? It was detected in the particular instance we showed there. There was discharge happening, and that was like in a solid insulation. So although it's a liquid insulation, we do tend to see that very much clustering. So the transient earth voltage detects it. So in those particular distribution type transformers, we do find quite frequently stuff that is occurring inside the oil as well as inside bushings or the cable termination itself. So it's detected in the same way using the transient earth voltage technique. And when we find something that we suspect as being oil, then we will recommend a DGA. Often with a distribution type transformers, people tend not to do routine DGA as they do for the larger transformers. For larger transformers, the TEV technique is not quite as easy to determine, although in principle, again, it will also detect problems inside there. How often do we need to calibrate the equipment? Typically, we say annual calibration of handhelds is the way forward, just to check everything is operating properly and correctly. You will generally see if you get a problem with equipment, you will generally see that it fails. If it fails, it fails obviously. So something that's drifting is not really going to cause you too much of a problem, because you're looking very much, is it in the green zone, the amber zone, the red zone? You don't have to be. The difference between something that is measuring 38 or 39 dB is not realistically critical 1 dB. It's all about the is it high discharge or low discharge? Where is it? What type of discharge it is? But if you calibrate that on an annual basis, then we tend to we pick up other issues maybe that with the equipment, and that's what we recommend. Got any more, Thomas?
No, I think you've covered the ones I haven't answered. I've just gone through and answered a couple that you weren't talking about.
Okay.
You do calibrate. So just if you do want to cover it, all the sensors are on the outside of gear. It doesn't need to be installed.
Oh, we got one more here. Or how susceptible is PD monitoring inspections to industrial electrical noise?
Yeah, so I did answer that.
Oh, you have answered that, yeah.
It's just we use aerials to exclude noise.
Yeah, so industrial noise is quite interesting. It can be very variable. Typically, we very rarely find a situation where we cannot carry out a good test with industrial noise. Electrical noise, maybe from VSDs and things like that, can cause interference. The fact that we've got the phase resolve plot helps against that, so we can see the difference between it. Electrical noise tends not to go up into the band where, or it's rare for the electrical interference to go up into the band where we get particularly concerned on the TEV side of things. Ultrasonically, the interference from ultrasonic is usually less frequent. We see that, and you can use different things such as shielding in that. For monitoring situations, we can actually deal with that. So if it is a very high electromagnetically noisy environment, then what we can do is put a monitoring solution around the switchboard, and we use aerials and time of flight presence detection to effectively mask out that, so we find things that are happening inside the switchgear and mask out everything that's coming from the outside. It's pretty unusual that you can for interference to cause you problems. There are times we've done it maybe in certain mine situations that we temporarily, without affecting production, turn off a VSD to have a cleaner test. But generally we can take things or carry out enough without too much of a problem.
The only other question would be, is it difficult to retrofit PD monitoring gear compared to installing it when the board's made? Just without gears on the outside.
Okay, yeah, retrofitting is very, very straightforward and easy actually. So you typically, most partial discharge monitoring systems do not put sensors or on certainly on air insulate or on lower voltage or medium voltage 33 kV and below. Typically, partial discharge monitoring equipment doesn't put sensors inside chambers. So retrofitting the transient earth voltage is retrofitted on the outside. Ultrasonic sensors are pointing towards gaps. HFCTs are on the cable sheets. Now, using HFCTs to monitor the cable and or the switchgear needs to go around the cable earth. So if that cable earth is inside the box, then that is the one situation where we do install internal sensors inside, say, the termination, by placing a HFCT around that cable earth. If the earth is not taken out and isolated from the gland to the outside, then absolutely you do need to go in there and do it. So sometimes it's a case of doing that in advance, or during an outage, it's a relatively straightforward installation if you do need to look at monitoring of cables. The transient earth voltage and the ultrasonic are non-intrusive anyway, and it's an easy retrofit.
Can you see the second last one?
I'm struggling to see the questions, to be honest with you.
It's just cable terminations after the shield is pulled down. How a PD will propagate in the insulation to the shield. So it's just something once the shields are off, why is the PD forming in terminations?
Oh, from the termination.
Yeah.
Okay, so when discharge is happening inside of a cable, you can find the signals on the conductor and on the cable shield in the opposite polarity. It's the reason why we can't actually put the HFCT around the whole conductor and the screen itself, because the signals will cancel out. So when we're testing cable terminations, in all honesty, if there's a problem inside the termination, then carrying out a transient earth voltage and an ultrasonic test on the cable itself is usually enough to find that the problem is happening there. The HFCT on the cable shield will find those signals as well, and depending on what sort of frequency band it is, you can indicate whether it's something that's coming up the cable or is at that termination itself. So the signals from the partial discharge will come onto the screen. They will also come from the switchgear down and impinge onto the screen, the shield of the cable. If it's from the cable itself, it will tend to be a unipolar pulse. If it's from the switchgear, it tends to be a bipolar pulse. But all of these signals will come onto the cable screen, and if we've got that screen isolated from the conductor, and we haven't got multiple paths into earth, then using that HFCT or RFCT is able to distinguish which one or what type of discharge it is and how big that is. Does that answer that?
Yeah, and then this is one we can answer privately, but we should be good an hour on the dot.
Effective range of measurement, is that one we've answered?
Yep. Oh, you go through, I haven't answered that.
Okay, what is the effective range of measurement? That just depends on the technique and the problem. So if we're looking at ultrasonic and you use a parabolic dish to test the overhead termination, then ground level detecting overhead termination is not usually a problem. So we're talking, a few tens of meters in that particular instance. Transient earth voltage signals will travel. Sometimes we've actually found a problem a couple of 100 meters away from the actual source. So for measuring at the switchgear and measuring at a particular switchgear and finding that the actual problem was coming in from a couple of 100 meters away on the next ring main unit upper feeder. So signals will travel on the VHF range, which is TEV. UHF range signals will travel a lot less. But that again depends on how open things are. If you're using UHF sensing techniques in metal clad switchgear, then they won't travel at all. If you're on an open terminal type switchgear, signals in the UHF, VHF, HF range, all of those signals, electromagnetic signals, will travel good distances. So you can find things away. So for example, on one overhead problem that we found, we were finding, even using the UHF technique, which UHF signals will attenuate quicker, sometimes up to about 3 spans away from the fault. We were finding that using a directional antenna and UHF. So it just depends. The HFCT on the cable is another one. How long can you see down the cable? That can be, depends on the size of the discharge, depends on the type of the cable and the amount of noise on the earth, but measuring and finding problems 3 or 4 kilometers down a cable is absolutely been done many times. So it's we need more specific questions to answer on that one. It's very dependent on the type of discharge and the technology you're using in that particular instance. Okay, what else have we got?
That's it. I'm just answering the last one now.
Okay.
I'm just answering the last one now.
Where does the majority of cost, have we done that one?
Oh, I'm typing it now. You can go through it if you want.
Okay, where does the majority of cost to customers come from? Online PD equipment or data analysis and expertise? That's an interesting one. Thank you, Kyle. It's quite a simple technique to deploy. So online PD equipment is actually taking the measurements is relatively straightforward. Using the capacitive probe, using the ultrasonic sensors and things like that. What really needs to be done to get the best value of that is to do that in a very good logical manner. And the value is probably coming from the data analysis and the expertise. So as an organization, we EA technology, for example, we will carry out service contracts for people. We will also look at people's results where they come in, where people want an opinion on that. So that's where some of the value is. The cost of deploying this is still a small fraction of allowing a failure to happen. So I think it's all very, very valuable. The best value is to get the right answer quicker. So we've had situations where somebody has taken measurements and absolutely taken measurements well, found that there was an internal type discharge, and then replaced the termination on the back of it, and had not gone that extra step to trace that down to what was actually coming from a nearby transition joint from a XLP to paper lead cable. So the cost of actually fixing a problem that actually wasn't the problem and not addressing the right thing was the issue there. So the more expertise that you have, the better data analysis, then often you can get to the answer a little bit quicker and a little bit cheaper. But the actual deployment of this is not particularly expensive, and solving one failure is certainly a very, very easy and quick payback exercise. I think we've answered them all, have we?
Yeah, that's all of them in my books.
Okay. So thank you very much for people attending. You have the contact details there. If you do want any other questions, any follow-up, feel free to do that. An article, some question and answers will be posted out with the link to the recording for this as well. So thanks for attending. Keep an eye out for our next, and good luck. Stay safe. I'll find out what the top is.